Hi, welcome back. This is Professor Ridge, and today's lesson is on section 8.5, combinatorics, permutations. So the study of permutations involves order and arrangement. So order and arrangement. The fundamental counting principle. So given a combined action or event, that's a keyword, in which the first action be performed in n sub 1 ways, the second one n sub 2, so on. The total number of ways in which the combined action can be performed is the product, n sub 1 times n sub 2 times n sub 3 up to n sub k. Okay, so you just take the product of all the number of ways. Let me give you an example. Alright, so how many four-letter code symbols can be formed with the letters A, B, C, D, E, F with repetition? That means allowing letters to be repeated. So by fundamental theorem here, we got 4 spots for four-letter code. So I can put A, B, C, D, E, or F, which is 6, in each of the spots, since I can have repeats. Now, it doesn't have to be repeats, but I could have repeats. So whatever 6 to the 4th is. So I get 6 times 6 times 6 times 6. So that's 1296 ways, right? And then B, without repetition, meaning you can't, once you use a letter, you can't use it again. So then our idea is going to be you can use A, B, C, D, E, or F, that's 6. But once you use the letter, you can't use it again. So then you're going to do 5, then 4, then 3. And then that is equal to 360. See, quite a bit less when you put that restriction on. Okay, so now a permutation of a set of n objects is an ordered arrangement. That's key there, ordered arrangement of all n objects. So the next section we're going to talk about combinations, and the difference between permutations and combination is order matters for permutations. Combinations, the order doesn't matter. Okay, so that's a distinction you have to keep straight. Okay, so find the number of ordered arrangements of set A, B, C, D. So again, we're looking for the number of permutations. That's the same thing as saying find the number of ordered arrangements. So if you know it, you can have A, B, C, D. You can have B, A, C, D. You can have B, C, A, D. You can have B, C, D, A. You can have, let's see, A, B, D, C. Okay, so I went ahead and wrote them all for you so you can see. Now we can do it, we didn't have to list them all this way, find all the permutations. We could have used the fundamental theorem counting. So we wanted 4 spots, because there's 4 numbers in our set, 4 letters in our set. And for the first one, we could have chose 4, A, B, C, or D. For the second spot, once you use one of the letters, you can't use it again, right? Because we're just rearranging the set of 4 letters. So it's just like we did up there without repetition. So now you have 3 for the second spot. Now you only have 2 letters left for the last spot, the third spot, and 1 letter for the last spot. So that's going to give you 24 permutations. Okay, which I listed all 24 there for you to see. And you see that the order doesn't matter. A, B, C, D is different than A, B, D, C. Alright, so the order matters. That's permutation. Okay, so the total number of permutations of n objects, denoted n Pn, that's why we say it, n permute n, is given by n, pn, so it's sub n, or subscripts, the n's, equals n times n minus 1 times n minus 2 times n dot 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 times 3 times 2 times 1. So an example would be, so find 5 permute 5, so that's going to be 5 minus 1, 5 minus 2, dot, 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 until you get to 3, 2, 1. So see, you're just subtracting 1. So 5 times 4 times 3 times 2 times 1. So obviously that was in there already. And then that's going to be equal to 12, 24, 120. Okay, so that brings us to factorial notation for any natural number n. N with the exclamation point, we read that as factorial. So n factorial equals n times n minus 1 times n minus 2, so on until you get to 3, 2, 1. So you end at 1. And just by definition, we're going to define 0 factorial is just 1. Okay, so that's by definition. Okay, so note that npn is equal to n factorial. Okay, evaluate 7 factorial, so that's 7 times 6 times 5 times 4 times 3 times 2 times 1. Punch that in your calculator. Hopefully you have that button. If not, you just have to do it by hand then. Okay, so that's 5,040. Now note, we just did 5 factorial, so 7 factorial is 7 times 6 times 5 factorial. So, we did 120, so if you did 42 times 120, you should get 5040 also. Okay, so if I were to do this one, 9 factorial divided by 4 factorial, what I do is I'm going to go 9 times 8 times 7 times 6 times 5, and at any point I can stop and say, okay, I get tired of this. I can do the 4 factorial. And the reason I'm doing that is because on the bottom I can cancel that out, and now I just do 9 times 8 times 7 times 6 times 5. 72 times 42 times 5 is 15,120. So 15,120. Okay, now 8 minus 5 in parentheses factorial. So you still do order operations. You're going to do the grouping symbol first. That's going to be 3 factorial, which is 3 times 2 times 1, which is 6. Okay, so now on to permutation of a set of n objects taken k at a time. And that's an ordered arrangement of k objects taken from the set. And the number of permutations for this situation is denoted in pk, n permute k, and that's given by the formula n permute k equals n times n minus 1 times n minus 2 dot dot dot, and you're going to stop at n minus k minus 1 in parentheses, and that's equal to n factorial over n minus k factorial. So let's try some of these examples. Okay, so how many permutations are there of the letters of the word combines if the letters are taken 5 times? So basically we're saying, what are 5? There's 2 ways to do this. We can use the fundamental theorem of counting. Okay, 2 ways to do it. Okay, so there's 1, 2, 3, 4, 5, 6, 7, 8 letters. So I can put 8 letters for the first one, 7, 6, 5, 4, and then multiply that out. Or I can say I'm going to do, there's 8 letters, and I'm going to permute 5 at a time. 8 permute 5, and then that's going to be 8 factorial over 8 minus 5 factorial, which is 8 factorial over 8 minus 5 is 3 factorial, which equals 8 times 7 times 6 times 5 times 4 times 3 factorial. Remember, at any time you can stop and write factorial, and see, you get the same result. So whatever 8 times 7 times 6 times 5 times 4 is, which should be, just did it, 6,720. Okay, so you can do it either way. So that's the idea of learning this new terminology, the permutations. So it's 8 permute 5. Okay, so note the number of distinct arrangements of n objects taken k at a time, allowing repetition, is n to the k. So, you can take, so like if we did this, the one above, where you can use any of the letters and repeat it, it'd be 8 times 8 times 8 times 8 times 8, so it'd be 8 to the 5th. So here's an example of how many distinct 4-letter words, I'm putting words in quotes, can be created using the English alphabet. So, A is not a word, but, I could define it and it could become a word, right? So that's what I mean. So it's not necessarily a word that's in the dictionary, just what are 4-letter combinations that I can create using the 26 letters in the alphabet. So again, it's going to be, I can pick any of the 26 letters, and since I can have repeats, and then the little note that we wrote up there, the shortcut would be, well, we want 4-letter words, so it'll be 4 to the 26, it'd be 26 to the 4th power. And you just punch that in your calculator, and it's quite a bit. So 26 to the 4th is 456,976. Right? And obviously we don't have that many 4-letter words, but that's how many 4-letter words we could create if we were allowed to use 26 letters. Okay, so for a set of n objects in which n sub 1 are of one kind, n sub 2 are of another kind, and n sub k are of a kth kind, the number of distinguishable permutations is n factorial over the product of n sub 1 factorial times n sub 2 factorial times n sub k factorial. So let's look at an example. In how many distinguishable ways can the letters of the word mathematics be arranged? So if you look, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so I'm just rewriting the formula down here. So that's going to be 11 factorial over, now look, there's, for m, there's 2 m's. For a, there's 2 a's. T, there's 2 t's. H, there's 1. E, there's 1. So we got M, we got A, we got T. I, there's 1, and C, there's 1, S, there's 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just making sure I got them all. So we're going to go 2 factorial times 2 factorial times 2 factorial times 1 factorial, 1 factorial, 1 factorial. I don't really need to write the 1 factorials. I'm just emphasizing the formula. 1 factorial. 1, 2, 3, 4, 5, 11. Okay, so that's going to be... Okay, so I get 6,652,800 distinguishable permutations of mathematics. So if you switch the m with the m, since you can't tell the difference which one was the first m and which one's the second m, you would double count that. So that's why we're dividing out the 6 things. And the same with the t's. If you switch to 2 t's, you can't tell the difference which one was the first t or second t. So that's another one that you double counted. So you got to divide those out. All right. So that concludes the lesson for 8.5. Go to My Math Lab, complete your exercises there. See you next time.